So, welcome to video number 4 in this introductory module. And in this video, we're going to talk about LC3 or limestone calcined clay cement. So what is limestone calcined clay cement? Well, this is actually a family of cements, and often we talk about LC350 or LC365. The figure in this case refers to the clinker content. So here we see on the left, we see the composition of ordinary Portland cement, where we have about 95% clinker and 5% addition of calcium sulfate or gypsum. When we have typical Portland Porcelainic cements, as shown here, we will have about 70% clinker and about 30% of pozzolan, which can be typically something like fly ash, but can also be calcined clay. And usually, because of the reactivity of these pozzolanic additions, 30% is the maximum level of addition we find in practice. However, what's very special about the LC3 family is now, instead of adding just calcined clay on its own, we add calcined clay together with limestone. And what we find is that we can add an extra 15% of limestone, we can remove 15% more of the clinker, and we can get the same performance as in the pozzolanic case here. So on the right, we see some strength results for LC350. You see at 1 day, the strength is somewhat lower than it was for the ordinary Portland cement, but already by only 7 days, the strength of the LC350 system has surpassed that of the ordinary Portland cement, and it's still higher at 28 days. So this is quite remarkable because it means for only 50% of the clinker, we have the same performance. This also means we have about 30% less CO2. We get, as I said, similar strength. And in some respects, we have quite a big improvement in the properties, particularly in respect to chloride penetration and to alkali silica reaction. So in this module, what we're going to talk about is what types of clays can be used, how they can be calcined, and where we can find the kind of suitable clays in the world today. So what we see in this slide here are the crystal structures of the basic clay types. All clays are layer structures. So here we see the layers, and these layers are aluminosilicate layers. So we see the orange dots represent the silicon atoms, which are found in little tetrahedra, so in a little cage of oxygens, and the green atoms represent the aluminium, which are found in octahedral cages of oxygen. Now, the two materials on the left here, the ilites and the montmorillonites, are what's called 2-to-1 clays. And what this means is that we have 2 silicate layers here and here, which sandwich the aluminium layer in the middle. And the difference between ilite and montmorillonite is mainly in terms of the ions that are found between the layers. That montmorillonite usually has alkali ions and more water between the layers. And finally, on the right here, we have the kaolinite structure, and the kaolinitic clays are what's called 1-to-1 clays, and this means in the layers we have 1 layer of silicate and 1 layer of aluminate. In this slide here, what we see is the thermal decomposition of the different clay types. And we can see that these have a thermal decomposition in different ranges. What these peaks represent, they represent the amount of heat that is absorbed by the material as it's heated up. And this heat is absorbed due to the loss of hydroxides from the structure, which is called dehydroxylation. And we can see that these different clay types have dehydroxylation in different temperature range. The clearest dehydroxylation is this one here for the kaolinite, which occurs between about 450 and 650 degrees. And this Signature provides a very good way of determining how much kaolinite you have in any clay you may want to investigate. All you do is to make this kind of thermal decomposition. You can even quite simply do it by heating your material in two different ovens, one at say 400 and one at 700, and looking at the weight loss between these two temperatures. Of course, as you can see, there will be a small interference if you have also some eyelite in your sample. But these kind of effects can be determined by looking at something like an X-ray diffraction diagram. If we look in the electron micrograph, we can see this layered clay structure. We can see that the clay is made up of little platelets. Here we see the raw clay before dehydroxylation. Here we see the clay after dehydroxylation. Basically at this level in the SEM, you don't see any change in the morphology. It appears to be very similar. We have to use other techniques to really see what's happening within the crystal structure. And particularly useful in this regard is solid state NMR when we study 27 aluminium ion. So nuclear magnetic resonance, or NMR, is a technique that can be used to look at the local environment of a particular species. So we see for the 2:2:1 clays, iolite and monmorillonite, that as we heat these materials, we get a transition of the aluminium from the octahedral coordination in the raw clay. Octahedral has 6 apexes, so this is also called a 6 coordination, to a tetrahedral coordination or a 4-fold coordination. What is quite clearly different in the kaolinitic clays is that as well as this shift from octahedral coordination to tetrahedral coordination, we see quite clearly the emergence of this 5-fold coordinated site. And this 5-fold coordinated site is the indicative of a disordered or semi-amorphous site, which is what means that it's easier for it to react. So this is the very important difference that happens in thermal decomposition between the 2:1 clays and the 1:1 kaolinitic clays. The 1:1 kaolinitic clays have this disordered aluminium, which is then the atoms that can go on and react with our cementitious materials. Here we see the appearance of these calcined clays. Depending on the other materials that are present in the clay, the colour of the clay can change over the whole spectrum from white to a reddish colour if there's a lot of iron oxides present. You can actually control the colour that comes out in the end by the conditions of oxidation and reduction in the kiln. Okay, in this slide here, what we see is the Porcelainic reaction of these different clay types in cement. So the Porcelainic reaction basically involves the reaction of the porcelain, the calcined clay in this case, with calcium hydroxide that comes from the cement. And this code here, K stands for kaolinitic, I stands for ilitic, M are the monmorillonite clays. And as references, we've got the plain OPC and the plain OPC with just an inert filler, which in this case was quartz. So we can see how the different clays react by looking at their consumption of calcium hydroxide relative to the amount of the cement, the clinker-based cement, OPC. And in most cases, we see that the amount of calcium hydroxide produced is actually somewhat higher than the reference, which is this curve in black, which is the plain Portland cement. And the amount of calcium hydroxide is somewhat higher purely due to a filler effect, as in this grey curve here, where the fact that you have a dilution of the cement by the clay gives a bit more room for the cement to react, so it produces a bit more calcium hydroxide. In sharp contrast, we see the kaolinitic clays here, we have much lower calcium hydroxide contents. This calcium hydroxide content becomes gets lower and lower with time, and this is a typical signature of the pozzolanic reaction of the calcined clay. Even at very early ages, we can see the calcium hydroxide content is very much reduced compared to the Portland cement reference. Finally, we perhaps want to look at this monomeritic clay here, which does seem to show some reaction at later ages. What should be the optimum temperature for the calcination? In this graph here, we see for a particular clay that has been calcined at different temperatures, how the strength varies over time. So the different temperatures we've used are the plain raw clay with no calcination at all, 600, 700, 750, 800, 850. And the raw clay, it's just reacting as a filler, so you see the strength development is really quite poor. The calcined clays, even from 3 days, are giving a very significant increase, which is indicative of their reaction. And we see by 7 days that for this particular clay, which contained about 40% kaolinite, if you're for the optimum calcination temperatures, the strength is surpassing that of the Portland cement. We see that the strength is increasing from 600 to 700 to 750. 800 is about the same, and by the time we get to 850, then we see in this particular case the strength is going down. And this is what we've observed in most cases, that the optimum calcination temperature is in this range 750 to 800. It may be somewhat lower if you have small content of calcite in the clay. Instead of having to do this series of strength tests, what we see on the right is the results of a reactivity test, which we'll talk about later in the series. And here we can use much smaller amounts of clay and study the heat evolution in what's called a calorimeter. But we can see the same trend. We can see the raw material basically has no reactivity. At 600, we get modest reaction. This increases through 700, 750, 800, and then by 850 there's a clear decrease in reactivity. Now, why do we have this decrease in reactivity? We can see that in this series here. This is the clay calcined at 600. We can see these agglomerates of these tiny clay platelets. Again, we can see these agglomerates at 800. And now when we go at higher temperatures, in this case we've gone right up to 925, we now can see that we no longer see these individual platelets, but we see these kind of glassy looking grains. And what's happened is we've had a small amount of liquid phase forming, which actually sinters these clay particles together. And if we have this happening, then we may get we'll get a very strong decrease in reactivity. So the critical question now is, what grade of clay do we need to be able to make these LC3 materials? So at EPFL here, we've studied a wide range of clays from around the world. These clays had different origins. Some came from Latin America, some from India, other parts of Asia, etc., even from Europe. And the fineness of this clay, the production method of this clay, the different, the minor phases that were present in addition to the clay, all of these varied quite widely between the different materials. But we calcined all of these. If they weren't calcined, we calcined these clays, and then we used them in the LC350 system and measured their strength in the European mortar bar test. And what we see quite clearly here is that we get a very clear correlation between the calcined kaolinite content, that's the amount of kaolin which was in the original clay that had been broken down during the calcination, between the calcined kaolinite content and the compressive strength development. So we have different curves here for the different ages, for 1 day, for 7 days, 3 days, for 7 days, 28 days, 90 days. And in addition to this strong correlation with the calcined kaolinite content, we've indicated here by this dotted line, we've indicated the reference strength of the plain Portland cement. So you can see that at 3 days, if you have a kaolinite content of over 80%, you can meet the same strength as your ordinary Portland cement. Whereas if you're prepared to wait a bit longer, to about 7 days, then if you have a kaolinite content of between 40 and 50%, you will get a similar strength to your ordinary Portland cement. So this is very important because it means for this LC3 system, we don't need to use very high purity clays. High purity clays, notably used to produce metakaolin, have to have very strong requirements for color, for purity, etc., which makes them very expensive. Whereas these kind of clays, which contain much lower amounts of kaolinite, only say 40–50%, are generally waste materials, which are consequently much cheaper. So the kind of clays we want to use are very widely distributed around the earth. And this is a soil map which gives an indication of what kind of clays you're likely to find below the surface. And it's a rather simplistic representation, but we can be quite sure that in all the regions where we have this yellow color or this pink color, there we will certainly have abundant clays. And we see that this is really very, very widely available in this central equatorial subtropical region going through China, Southeast Asia, India, Africa, and Latin America. And in fact, we've seen in India, where we've made much more detailed studies, that suitable clays are not confined only to these yellow and pink regions, but we actually have very large amounts of suitable clays. For example, in this region of India, in Gujarat and Rajasthan, which on this soil map would appear not to be so suitable. So what's the main message here is the kind of clays we need are incredibly abundant throughout the world. The reserves are virtually unlimited. These are just the countries in the equatorial subtropical regions where the growth in demand for cement is strongest. And in many of these countries, what we can find is that the suitable clays are currently stockpiled as waste. So this picture comes from a quarry in India. This is a quarry where they're extracting high purity clay for producing metakaolin, which is then used for ceramics or in the paper industry. And this huge mountain here is just waste. This is material which has too low quality for exploitation at the present time. But this waste here is a very suitable quality for blending with cements. And we've taken those kind of waste materials, we've made full-scale trial productions. This just shows a couple of houses produced from these productions. This one in Cuba here, this one in India. All the materials, the concrete blocks, the render, here the roof tiles, etc. These are all produced with LC3 material. And they were actually produced, they could be produced by totally unskilled workers in the same factories with no special training, just purely with a one-to-one replacement, taking one bag of the cement that was used before, either OPC or Porcelainic cement with fly ash, and replacing that with LC3. And in this case, in India, we made a more detailed calculation of the CO2 savings, and we could calculate that about 7 tons of CO2 were saved just in this one single house by using LC3 materials compared to the existing materials. So let's look at what we've seen in this module. What we've seen is how we can use a combination of calcined clay with limestones to go to much higher levels of substitution than is typical in pozzolanic cements. We've seen that it's really the kaolinitic clays, which have the potential to give this high pozzolanic activity after calcination. And this high pozzolanic activity results from their one-to-one structure, which means we get poorly organized alumina after calcination. The optimum temperature for the calcination is in this range 750 to 850. If we go to higher temperatures, then we may get sintering and loss of surface and reactivity. If we look at the performance in mortars and concretes, we see that if we've got more than about 40% kaolin, these can be very suitable for use in LC3 blends. Even in a mixed system, you can get a similar strength after about 7 days, and we're sure you could get even better earlier strengths by optimizing the grinding parameters. These kind of clays with 40% or more kaolinite are very widely available around the world, particularly in the regions where the growth in demand for cement is highest. And we've made trial productions of LC3 in both Cuba and India. So this short video completes the introductory module. I hope that you will be interested to come back and listen to the module on hydration, which follows this.